This is Physics 1020 and 1090. This lecture is for Monday, April 13th. We're in Chapter 29 on nuclear physics. This is the second video in which we talk about nuclear fission. Okay, where's the story? Left off. The story had us bombarding different elements with neutrons. And in Germany, there was work being done by two German scientists, Otto Hahn and Fritz Strassmann, and an Austrian scientist, Lisa Meitner. And they were bombarding uranium with neutrons. And they were seeing radioactivity released, and their hypothesis was that a neutron was coming in, hitting the uranium, and chipping off a couple alpha particles, and leaving you with radium-228, which was then radioactive, and you could produce a artificially radioactive isotope. So this was their hypothesis, and to test that, what they were going to try to do is take the uranium and remove all the other elements they could find and see if they could get down to just pure radium. So they began to do chemical separation. You can laboriously separate different chemicals, and you could see, remember, radium is radioactive, so you could see if the radioactivity went with the other elements or went with the radium. And they separated out, and the radioactivity always stayed with the radium until they finally got down to just two possibilities. They got to radium and barium. And radium and barium are in the same column of the periodic table, so they're very hard to separate. But they tried, and they couldn't separate the radioactivity from the barium. So they ended up publishing this weird paper that says, as chemists, we think this radioactivity is associated with barium. But as physicists, we know it's got to be radium. All right, so here's the story in 1938 that they cannot separate the radioactivity from barium, but they don't quite understand what's going on. Now, Meitner was Austrian, and in 1938, the Anschluss happens, where Germany annexed Austria. If you ever watched Sound of Music, you may remember Captain von Trapp tearing down the Nazi flag and ripping him up. Well, he was an Austrian, patriotic Austrian, who objected to the Anschluss, but whatever happened, Germany took over Austria. Now, Lisa Meitner had been working in Germany, and she was of Jewish descent. She wasn't a practicing Jew, but she had ancestors who were Jewish. And of course, in Germany at that time, that was a major problem, and people were being arrested and taken away when they were of Jewish descent. Lisa Meitner had been protected because she was an Austrian citizen, and it just for them to take her and arrest her would have caused an international incident. But once Germany annexed Austria, that protection no longer existed. So Meitner realized she had to flee Germany. So the story of her escape from Germany is actually rather dramatic, but we don't have time to go into it all today. But she escaped Germany just at the last second, hours ahead of the Gestapo, who was going to arrest her. And she went off and eventually settled in Sweden. Now, Meitner was in Sweden alone, but she had a nephew, and the nephew came to visit her in 1938, right around the Christmas season. And on Christmas Eve day, Meitner and her nephew Otto Frisch decided to go out and take a walk in the woods. Now realize, Meitner had been in contact with Strassmann and Hahn, talking by letters, and they had traded letters. She was aware of all the experiments that were still going on, and she couldn't understand them. So she and her nephew went out into the woods. He was on snow skis. She was just walking along next to him. They sat down in the snow in the forest. They got a scrap of paper and they started talking. And they realized this might be happening. You might have a neutron come in, hit uranium, and break the uranium atom into two pieces. One piece could be barium, and one piece could be krypton. If you add up all the numbers, also you would end up having to release 3 neutrons. This is nuclear fission, and this is what they figured out was happening out in the woods. Nuclear fission, where a uranium nucleus split into 2. Now, as you might guess, I'm going to read to you a little bit about nuclear fission, the conversation that went out in the woods Christmas Eve. They, that is, Meitner and Frisch, pictured the uranium nucleus as a liquid drop, gone wobbly with the looseness of its confinement, and imagined it hit by even a barely energetic slow neutron. The neutron would add its energy to the whole. The nucleus would oscillate. In one of its many random modes of oscillation, it might elongate. Since the strong force operates only over extremely short distances, the electric force repelling the two bulbs of an elongated drop would gain advantage. Let me show you the picture that they draw. This is a picture they were actually drawing on those scraps of paper out in the snowy woods. Two bulbs would push further apart. A waist would form between them. The strong force would begin to regain the advantage within each of the two bulbs. It would work like surface tension to pull them into spheres. The electrical propulsion would work at the same time to push the two separating spheres even further apart. Eventually, the waist would give way. The two smaller nuclei would appear where one large nucleus had been before, barium and krypton, for example. Barium and krypton. Then, Frisch recalls, Lisa Meitner was saying that if you really do form two such fragments, they would be pushed apart with great energy. They would be pushed apart by the mutual repulsion of their gathered protons at 1/30th the speed of light. Meitner and Frisch calculated the energy to be about 200 million electron volts, 200 MeV. So, we see that when the nucleus breaks apart, you now have two positively charged nuclei, and they're separate, so there's not the strong force holding them, so they would be repelled by each other and fly apart and give off kinetic energy. And they'd also give off neutrons. So this was what underlies nuclear fission. And news about this spread like wildfire, and it became all the rage. At the same time, 1938, Germany, remember, had annexed Austria, now annexed parts of Czechoslovakia. And this caused a great debate within the international community and almost led to war at that time. But finally, Germany promised not to do it again, and France and England gave in and let Germany annex parts of Czechoslovakia. But realize that people understood that uranium fission would give off huge amounts of energy and could possibly be used for nuclear weapons. Also realize that this work that had been done specifically on fission and nuclear physics in general had largely been done in Germany. Now let's come to Niels Bohr. Niels Bohr, in 1939, through theoretical reasoning, figured out that there's two isotopes of uranium, 238 and 235, and it's the 235 that undergoes fission. Why? Well, because remember, a while back we talked about how nuclei are somewhat more stable if they have two protons and two neutrons than if they have an odd number of protons and neutrons. Well, uranium-238 has an even number of protons and neutrons. It's a little more stable. Uranium-235 has an odd number of neutrons. That makes it a little less stable, a little more unstable. And it's just enough unstable that a single neutron coming in can cause it to break into two and undergo fission. Sometimes we say that uranium-235 is fissile. It can undergo fission by a single neutron. Well, Niels Bohr figured this out, and this has implications, because if this is what's causing nuclear fission, and 98% of uranium is 238. Only 2% is 235, but the 235 is what causes fission. Then what you really want to do if you want to have a nuclear reaction that gives off a lot of energy is you want to separate the uranium-235 from uranium-238. And in fact, this becomes an important part of the development of the atomic bomb. Uranium-235 is what you need for effective fission. Now, what about those three neutrons? Remember, when a neutron comes in, hits uranium-235, it breaks into two pieces and gives off three neutrons. Well, those neutrons can go hit other uranium-235 nuclei, and they can cause these to undergo fission. They'll break into two pieces, plus each of them will give three neutrons. Now you have 9 neutrons. Those 9 neutrons can go up and hit uranium-235 nuclei. Each one can hit and split uranium-235 and then give off 3 each. Then you have 27 neutrons. In the next generation, you have 81, then 243. And you can see that's growing dramatically and very quickly. It wouldn't take too many generations till you give off a huge amount of energy, very suddenly and dramatically. Each uranium fission gives off 200 MeV, which is a huge amount by atomic standards, not that much by our standards, but when you multiply it by giant numbers of generations, you can get a huge amount of energy. And this is what underlies the atomic bomb and our nuclear reactors, is this nuclear chain reaction. So once you start it, it can grow exponentially. Well, scientists realized that this could be the source of an atomic bomb, and they also realized that Hitler could use it to build an atomic bomb. So they were very worried that Hitler would get the atomic bomb and then he'd take over the world. So Albert Einstein, who was over in America by this time, had escaped Hitler. He was also Jewish. He had escaped Hitler earlier on. Wrote a letter to President Roosevelt. He was so famous that Roosevelt would pay attention to him, urging him to start an atomic bomb project in the United States to try to prevent Hitler from getting the atomic bomb and us not having any way to oppose that. So we start now, the United States starts the Manhattan Project. That is the project to build the atomic bomb. In the meantime, Hitler, after promising, no more trying to take over countries, first took over the rest of Czechoslovakia, and then he invaded Poland. When he invaded Poland, that triggered World War II. England and France declared war on Germany. World War II began. Well, at that point, Enrico Fermi comes back in the story. And Fermi was one of these scientists who had escaped, not Germany, but Italy, come to the United States. And Fermi had realized that fission, nuclear fission, works best with slow neutrons. The reasons are a little complicated, but fission works better with slow neutrons than with fast neutrons. So what you need is some kind of moderator. A moderator is a substance which slows the neutrons down. So Fermi's job, as part of the Manhattan Project, was to build a functioning nuclear reactor, the first nuclear reactor ever built. And it really consisted of a pile, that is, a pile of uranium surrounded by graphite. Graphite, a form of carbon, is what he used for his moderator. So he had uranium and graphite, and he could control this so it wouldn't explode using cadmium. Cadmium absorbs neutrons, so it'll suck the neutrons out and stop the chain reaction. So he had cadmium control rods controlling a mixture of uranium and graphite. He built this thing in Chicago, in a squash court underneath the Chicago University Stadium, and it was the first nuclear chain reaction. It was a little bit dangerous. If something had gone wrong, there had gone Chicago. But Fermi went on, and the story of Fermi and the first controlled nuclear chain reaction is a fascinating one. And so once again, I want to read a little bit about Fermi and chain reaction from the making of the atomic bomb. So here's an eyewitness account of what happened the day they actually pulled out the cadmium control rods and tried to see if they could get the chain reaction just to begin to go. They wanted to have it just on the edge so it would begin to build up, but very slowly. At first you could hear the sound of the neutron counter, clickety-clack, clickety-clack. Then the clicks became more and more rapidly, and after a while they began to merge into a roar. The counter couldn't follow anymore. That was the moment to switch to a chart recorder. And when the switch was made, everyone watched in sudden silence, the mounting deflection of the recorder's pen. It was an awesome silence. Everyone realized the significance of that switch. We were in the high-intensity regime, and the counters were unable to cope with the situation anymore. They couldn't count all the neutrons being produced. Again and again, the scale of the recorder had to be changed to accommodate the neutron intensity, which was increasing more and more rapidly. Suddenly, Fermi raised his hands. "The pile has gone critical," he announced. No one present had any doubt of it. Critical, meaning it was a controlled nuclear chain reaction. Fermi allowed himself a grin. He would tell the technical council the next day that the pile achieved a K of 1.0006. Well, this K was a parameter that told you whether you had a growing nuclear reaction or not, chain reaction. And 1 was when you're right in equilibrium. So they had just barely above 1, a very, very slowly growing nuclear chain reaction. Its neutron intensity was then doubling every 2 minutes. Left uncontrolled for an hour and a half, that rate of increase would have carried it to 1,000,000 kilowatts. Long before so extreme a runaway, it would have killed anyone left in the room and melted down. Then everyone began to wonder why he didn't shut the pile off. Anderson continues. Anderson was the witness. But Fermi was completely calm. He waited another minute, then another, and then when it seemed that the anxiety was too much to bear, he ordered, "Zip in!" That was the cadmium rod. It was 3:53 p.m. Fermi had run the pile for 4.5 minutes at 1/2 watt and brought to fruition all the years of discovery and experiment. Men had controlled the release of energy from the atomic nucleus. So, that's the story of Enrico Fermi and the first controlled nuclear reaction. Now, let's remember, Bohr had found that it was uranium-235 that could undergo fission. If you wanted to create an atomic bomb, you wanted to have pure uranium-235. 238 just got in the way. In fact, it was actually a problem because 238 could absorb a neutron and take it out of the system. You wanted to have pure uranium-235. How are you going to separate 235 from 238? Well, in Oak Ridge, Tennessee, there was part of the Manhattan Project was to separate the isotopes using, remember we talked about mass spectrometers? Basically, you take giant cyclotrons and you use them to bend the path of these nuclei in a magnetic field, and they'll bend by different amounts depending on their mass, and you can separate uranium-235 from 238. There was a huge effort, took huge amounts of electricity, many people to separate isotopes. In fact, Germans said that they finally came to the conclusion that there is no way to build an atomic bomb unless you turn your entire country over to separating isotopes. And that is almost what the United States did in this project in Oak Ridge, Tennessee. I've heard reports that 10% of the electricity used by the United States was used at Oak Ridge to separate isotopes during those years. So they were able to separate uranium-235 from uranium-238. Now let's talk a little bit about the atomic bomb and how it was actually built. And this happened in Los Alamos, New Mexico, where many famous physicists went and gathered together to build the atomic bomb. Well, suppose you have a small piece of uranium. Small piece of uranium, you cannot have a neutron, would undergo fission, break the uranium into 2 pieces and give off 3 neutrons. If those neutrons could escape from the piece of uranium before they ran into another uranium nucleus, then that would not undergo a chain reaction. You wouldn't get an atomic explosion. However, if you had a bigger piece of uranium, before the neutrons could escape, they would ultimately run into another uranium nucleus because there's just more nuclei there. It's a bigger piece, and those would then split and they would go off and they'd start their own chain reaction, and you'd get an explosion. So this is called the critical mass, was just the amount of mass you needed to undergo the critical explosion. So you needed a critical mass of uranium-235. So here's how the first atomic bomb worked. You had a target that was uranium-235. It was a piece that was below a critical mass, but not a lot below, just a little below being a critical mass. And you had another piece of uranium-235 was like a bullet, and it was also just below being a critical mass. And you put this in a gun barrel, and you fired the gun, and it fired this piece of uranium-235 in at this piece. And when the two merged together and met, you then had above a critical mass. The chain reaction would start, and immediately you get a major explosion. And this was the type of atomic bomb that was dropped on Japan at the end of 1945 on Hiroshima, and helped end World War II. Now realize Germany by this time had surrendered, and it was Japan was our remaining enemy, and the atomic bomb was used against Japan. Okay, another piece to this story, and that is what happens if you fire neutrons at a mix of uranium-238 and 235. Well, some of the neutrons hit uranium-238 and get absorbed and become uranium-239. Uranium-239 will then, being neutron rich, undergo beta decay and go to element 93, neptunium-239. Element neptunium-239 is also radioactive, still neutron rich, and it'll undergo beta decay to what? Stop the video and figure it out. It undergoes beta decay and becomes element 94, which is plutonium-239. Now, what's interesting about plutonium is fissile. It's like uranium-235. It has an even number of protons, but an odd number of neutrons. It's just on the border of stability, and being odd makes it so if just a single neutron comes in, you will get a nuclear fission and can start a nuclear chain reaction. So this is another path to making an atomic bomb. Instead of using uranium-235, which had to be separated from 238 through a lengthy process, you create plutonium-239 and use the plutonium in the nuclear weapon. And up in Hanford, Washington, in Washington State, there was a big new nuclear reactors built, and its main purpose was to generate plutonium. And this plutonium was then used in a second atomic bomb. It was sent to Los Alamos, and they built a second atomic bomb. And the second atomic bomb that was dropped on Nagasaki at the end of World War II was a plutonium bomb. So we have atomic bombs work both on uranium and plutonium, ending the World War. Now, why didn't Hitler develop an atomic bomb? He had all these scientists who were just as knowledgeable about nuclear physics as the Americans and the British. In particular, Werner Heisenberg of the uncertainty principle, led Hitler's nuclear bomb project. It's not absolutely clear why he didn't develop an atomic bomb, but it is known after the war, Heisenberg and other nuclear physicists, German nuclear physicists, were captured, and they held in a building that had hidden microphones in it, and they listened to them talk. And there's a lot of talk by Heisenberg and the others about how they really didn't want to build the atomic bomb. They didn't want to give the atomic bomb to Hitler. But they also had a reason for saying that, because if they had built an atomic bomb for Hitler, that would certainly have been war crimes, and they would be punished. So they had a strong motivation to downplay their role. And nobody knows to this day exactly how close the Germans were to atomic bomb, but it's pretty clear that they weren't real close. They weren't right about to produce an atomic bomb. But there's an interesting side story. 1941, Heisenberg went to Denmark, which was being occupied by Germany, and met with Niels Bohr, who was basically, he wasn't captive, but his country was occupied. And he met with Bohr, and they had a discussion, and apparently things went bad. Realized Heisenberg had been one of Bohr's students, had worked with Bohr to develop the uncertainty principle, had worked with Bohr to develop quantum mechanics. They were very close. But they had a falling out at this meeting in 1941. It's not clear to this day what exactly Heisenberg asked of Bohr, but apparently Bohr did not like it. And the meeting has been turned in now to a play called Copenhagen. And if you ever get a chance, I want you to watch the play Copenhagen. Perhaps after the semester's over and you're still sitting at home and you've got some time, see if you can find it on Netflix or one of those things. You can see if you can find Copenhagen. There's a version of it that's made a movie, and it's got that guy who is James Bond. Daniel Craig plays Heisenberg. And I want you to watch it because I think you know enough nuclear physics now to be able to understand the physics of the play. But realize that this is not a documentary about physics. This is a play about the interactions between Niels Bohr, Werner Heisenberg, and the third person in the play is Bohr's wife, and how they interact. And it really goes over a lot of the things that we've been talking about. I'm going to send you a short clip from the movie, which you can find on YouTube. Unfortunately, I could not find the entire movie out on YouTube. Perhaps you can. So, one last homework assignment to be done when you can is to watch the play Copenhagen. And that brings us really to the end of our discussion of nuclear fission. And one reason that I've tried to read so much out of The Making of the Atomic Bomb is because I want you to appreciate how these nuke develops in science interacted with the developments in politics and military developments to come together in the 1940s with the Manhattan Project. Okay, what's next? Well, we really only have one day with new material left. We're going to talk about two things. We're going to talk about nuclear fusion, which is the opposite of fission. And then we're going to talk about the Chernobyl nuclear disaster and learn a little bit more about nuclear reactors. And that will end the new material. Then we'll begin reviewing for the final exam.